Question 2. So I'm heating up some water using methanol in a spirit burner. I've got the mass of the burner before and afterwards, so I could work out the mass of methanol. But to start off with, I'm going to concentrate on the beaker and the amount of water and the temperature rise. And I'm going to use Q equals MC delta T. The mass of the water I've probably got, yes, 100 grams. MC, the specific heat capacity, I've been given 4.18, so I must be using Q equals MC delta T. And the temperature changes are worked out for me as well, 38 degrees C. So my first thing that I've got to work out is Q equals MC delta T. 100 multiplied by 4.18 times 38 is 15,884. I can put a minus in front of it, so because it's exothermic, so minus 1,584 joules of energy are given out. I could convert that into kilojoules. Joules going into a larger unit value of kilojoules, you divide by 1,000, so that would be 15.884. I think I'll leave it as joules just for now, though, because I know that the moles of methanol I've worked out the mass of methanol. So the mass of methanol by taking 214.02, taking away 212.37, I've worked out that I've got 1.65 grams of methanol burnt. I know that methanol is CH3OH, that's a 14, add 3 ones, add a 16, add a 1, so it's got a relative formula mass of 32, and moles is mass divided by relative formula mass. I've got 0.0516 moles of methanol. So 0.0516 moles of methanol gives out 15,884 joules of energy. Now I've got to work out what would be given out if it were a kilojoule per mole. Well, this amount is very much less than a mole, gives out 15,884, so if I divide 15,884 by this small amount, it will tell me the number of joules of energy that would be given out if I had a full mole. So heat change per mole, I divide by 0.0516 and it turns out to be 308,000 joules for a mole of methanol burned. I can now divide that by 1,000 and it tells me it's 308 kilojoules now rather than joules per mole of methanol burnt. It's a minus number, so it's minus because the enthalpy change, then the enthalpy of combustion is minus because it's an exothermic reaction. Suggest a reason other than incomplete combustion or heat transfer why the students value. Well, there's 3 reasons really why you might get values different from the data book. The main one is heat loss, heat transfer to the atmosphere, heat loss. We can't use that one. The next one is that the fuel doesn't burn completely, incomplete combustion. And the third one is that the actual beaker itself, the copper container, actually absorbs some of the heat. So heating up the copper container will be another source of error. The uncertainty. The temperature readings from the thermometer in this experiment was plus or minus 0.025. That means that the thermometer can be 0.025 out. This gave an overall uncertainty temperature of 0.05. That's because you're taking 2 temperature readings. So you're taking a temperature reading at the beginning and at the end to work out the temperature change, and that's why they've doubled the error, because you could get an error the first time and an error the second time, and so those errors are cumulative, added together. So I've got an uncertainty of 0.5. Calculate the percentage uncertainty for the use of the thermometer in this experiment. So I now need to take, say I could be 0.5 degrees C out of my temperature change. My temperature change is 38. So I could be 0.5 divided by 38 multiplied by 100% is 1.3. I'm taking it to, these numbers here are to, this one's to 1 significant figure, this one's to 2 significant figures, so I'll take it to 2 significant figures. the 17 is to 2, the 38 rather is to 2 significant figures as well. So 1.3 is a reasonable sort of level of accuracy. The student said correctly that using a thermometer and an overall uncertainty of the rise of temperature of 0.5 was adequate for this experiment. So the thermometer has got an error on it, but the student said it was adequate for the experiment. Explain why it's adequate for the experiment. So even though the thermometer's got an error, there's probably a bigger error somewhere else, and the main errors are these three: incomplete combustion, heat transfer to the surroundings, or heating up the copper container. The main one is heat loss to the surroundings. So heat loss to the surroundings, heat transfer to the atmosphere, is your biggest error. So really this is insignificant in comparison to heat loss. The enthalpy of combustion of ethanol is minus 1371 kilojoules per mole. The density of ethanol is 0.789 grams per centimeter cube. Calculate the heat energy released in kilojoules when 0.500 decimeter cubed of ethanol is burnt. So why would they give you a density? Density is mass divided by volume. They've given you a volume, so they've given you density and they've given you volume. Density is mass divided by volume, and they've given you the density, they've given you the volume. They must want you to work out the mass of ethanol. That's the only way the only way that we could go if we've got density and volume. So what we've got to do is density is mass divided by volume, so mass is density multiplied by volume. The mass of the ethanol is 0.789. Now it needs to be, look, the density is in centimetre cubed, so we need to turn decimetre cubed into centimetre cubed. A larger unit going down to a smaller unit, like decimetre cubed going down to centimetre cubed, you multiply by 1,000. So 0.5 multiplied by 1,000 is 500. So density multiplied by 500 centimetre cubed is 394.5 grams. That's the mass of ethanol. Now I can always work out the MR of ethanol. So ethanol is CH3CH2OH. So when I work out the MR, it works out as 46. 2 carbons are 2 12s each. The hydrogens, so there's 6 hydrogens in there as 6 and a 16 for the oxygen, 46 for ethanol, and so I can work out the number of moles. 394 divided by 46, 8.576 moles of ethanol. Well, minus 1371 kilojoules are given out when I burn per mole when I burn 1 mole. So the question is saying how much energy would be given out if I burn 8.576. So it's minus 1371 kilojoules for 1 mole multiplied by 8.576, and it comes out as 11800 kilojoules of energy released. 3 significant figures, must be at least 3 significant figures, so I've got at least 3 significant figures here to match the 3 significant figures in my answer, in my question.